For population growth, some populations don't increase without bounds. They approach what's called a carrying capacity that we use the letter L for as time increases. The population can only get so big because of constraints on the environment. For this type of population growth, we use what's called the logistic differential equation. And this is the generic logistic form. dy dt equals k times y times 1 minus y over L. K and L being constants. We're going to walk through and solve this generic differential equation, and then we're going to look at a specific example for this. So this is a separable one. And in order to integrate this, we're going to need to find partial fractions for the left-hand side. When y is 0, we end up with that a is equal to 1, and then we let y equal L, then the a term goes to 0 and we get b equals 1 over L. Plugging those back in here, we're going to end up with the integral of 1 over y plus 1 over L minus y if we simplify that second fraction. We get the 1 over L minus y because we have 1 over L divided by so the L is actually down in the denominator. We're simplifying this one right now, and that becomes 1 over L minus y. So, now that we found our partial fractions, we can go ahead and integrate on both sides. And we end up with the natural log of y minus the natural log of L minus y. We come by that with a u substitution. It's because it's minus y equals kt plus c. And the two natural logs can be combined into one using properties of logarithms. But before we do that, to simplify things, we're going to divide everything by -1, which is going to change the order on the left-hand side. And make the right-hand side change signs. And then when we combine these together, we end up with the L minus y on top of the fraction. And we do this for simplifying reasons. Then we change to exponential form. And now it's a matter of solving this for y and simplifying. So we have L minus y over y equals e to the negative c, e to the negative kt. E to the negative c is just some constant. We can call it b. Where b is a real number. And then multiply both sides by y. Add y to both sides. Factor out the y. And then we divide both sides. And we end up with the general solution for a logistic differential equation being y equals L divided by 1 plus BE to the negative KT. And if we can remember this formula, cool. If not, we can go through this same integration process with a specific differential equation. And so in this we're going to look at introducing 40 elk into a refuge. We know the population after 5 years. It's believed that the environment can support no more than 4,000 elk. That's our L value. We can turn around and write, because there's this limiting factor, we can write that logistic differential equation dp dt equals k times p times 1 minus p over 4,000. And we want to find a model for the population. We want to solve this for p. If we can remember this form, cool. We can just plug our numbers in. And using those initial conditions, we can find b and k. Now, I want to go through how to integrate this again with the numbers plugged in. So we separate out our variables. And then we're going to have to do partial fractions again on the left-hand side. And the two partial fractions we end up with are 1 over p plus 1 over 4,000 minus p. And then integrating those two fractions, we end up with natural log p minus natural log 4,000 minus p equals kt plus c. Divide everything by a -1 and then combine the logarithms to get natural log 4,000 minus p divided by p equals -kt minus c, and now we change to exponential form. And again, I'm just going through this same separable differential equation with specific values plugged in, showing that we can do this without having to remember what that general logistic equation is. And now we go through the process of solving for p again. We take e to the negative c and say that's going to be that b value. And when we solve this, we get p equals 4,000 over 1 plus BE to the negative KT. And we now have to use those initial conditions to find out what B and K are to finish this. So when T is 0, P is 40. So we can plug that in, and we end up with 40 equals 4,000 over 1 plus B. B ends up being 99. Our second initial condition that we know is that after 5 years the population is 104. So P of 5 equals 104. We can use this to find K. To solve this, we would multiply both sides by the denominator, do some distributing, and get K by itself, and what we end up with is that K is approximately 0.194. So our equation for P is that it's 4,000 divided by 1 plus 99 e to the negative 0.194 t. And we can use this to find any time or any population at any given time. So we could plug in 15, we could plug in 10 years later, whatever we wanted to plug in. We could have accomplished the same feat by just starting with this and using those two initial conditions and our population. P equals 4,000 over 1 plus BE to the negative KT. We know that P of 0 is 40. We plug that in and we find B. Then we use P of 5. We plug that in and we find K. But if you can remember the differential form of the logistic equation, we can just do integration to both sides using separation and get our solution for the function. Have a nice day.